Okay, so you can start, so whenever you want. Thanks.
Thanks for this opportunity. Today I will be talking about my recent progress on entanglement phase transitions in higher dimensional lattice models, and that bears a holographic resemblance. And I hope it can stimulate some discussion with high energy people as well, because coming from a brief high energy background in my undergraduate, this looks very much similar to something in standard model, for example. So without further ado, I would start with a brief introduction of the motivation to study entanglement entropy in many body systems, and in particular the area law of entanglement entropy and its violations. In particular, I'll mention one simple example how one can have such high severe violations in terms of extensive scaling, and also why it is hard to generalize this into higher dimensions. And then I will spend some time talking about progress since 2012, where when Bravi, Movasa, Shur, Korapin, and Professor Fredkin made on this very physically reasonable model that also will allow it to be generalized into higher dimensions in terms of these Fredkin and Moskin spin chains, where my advisor Israel and I did a Q deformation generalization that showed an entanglement phase transition between different scalings as you tune the parameter.
I want to clarify. I want to clarify one thing. My name is Fradkin. The model is named after a computer scientist named Fredkin. It's a different person.
Yes, thank you for the clarification. Yes,
although
and also
you write a paper on that. Okay.
Someone gave a talk that's titled Friedkin, and Fredkin, all about things somewhat related to these models. And yeah, and we have been thinking about this generalization to higher dimensions in the background for about 5 years, until recently I realized there's a whole combinatorics community that have been studying pretty much the same thing in different language that already prepared all the ingredients for this to be possible to be generalized in 2D. So it really required a minimal amount of work from our side to make this happen. And finally, I'll give some summary and outlooks. So entanglement is a special feature of quantum system where part of the state of part of the system depends also on the what state the rest of the system is in. So you can take an example of one of the Bell states or EPR pair, where the spin on side A is entangled with side B. So to show it's entangled, you can take the density matrix, and in this spaces of up, down, up, down configurations, and then when you take the reduced density matrix by tracing, by doing a partial trace on subsystem B, where the information about which you ignore now, you get the mixed state that corresponds to a statistical mixture of having 50% chance finding the state of A in up and 50% chance in spin down. So these are like integrating out the degrees of freedoms on the rest of the system if you are more comfortable with the continuum field theory terminology. And these probabilities are called the Schmidt coefficients, which you can use as a probability distribution to define a von Neumann entropy, which for pure state, it can only come from the entanglement. So this is some quantification of the entanglement that can also apply to a many-body system. In particular, in more generic systems, you need to, so this reduced density matrix, you need to first do a singular value decomposition to rule out things like a product state which is unentangled. And this will probably be the most technical part of the rest of the talk, but if you just can understand it for a few body system where you need to rotate the basis to find exactly what contributes to the entanglement, then all this is encrypted in this singular value decomposition called Schmidt decomposition. So it is known that thermal entropy is an extensive quantity, and so is a random state in the Hilbert space of many-body systems. The entanglement entropy also scales as the volume of the system. However, in the ground state of gapped local Hamiltonians, the entanglement obeys area law, and this can be understood as there is a range of correlation between the degrees of freedom in a many-body system, and as you increase the segment where you take you compute entanglement entropy of, it grows as the logarithms of the system size up until the correlation length, which is related to the mass of the quasi-particle, and then it saturates. So if you take the system to be arbitrarily large, then the entropy is bounded by one-dimensional smaller, by the system size of one dimension smaller, except at the critical point where the correlation length diverges, so that you have this logarithmic violation of the area law. And it has area law, I believe is first this term is first coined in black hole entropy, and it has importance in terms of finding efficient numerical simulations, because when area law is satisfied, you can essentially describe this. You can simulate with low cost corresponding to the bound dimension of this matrix product state, and also is important in the definition of topological entanglement entropy, which is related to the quantum dimensions of the particle content of a topologically ordered phase. So,
sorry, can you go back to the previous transparent? Yeah. So I don't agree with something you said here. In a general critical system, it's not obvious that you will have this log in it. So in 1+1 dimensions, so when the space dimension is 1, the entropy is just logarithmic. Okay, and that work by Halsey, Larsen, and Wilczek, and others. The work by Jove and Klisch is for the case of a system of free fermions at finite density.
Yes.
It's not actually, it's not a critical system. It's massless, but it's not critical. In critical systems, there is an area law, and then there is a subleading universal term. but it's
I
not.
see, I see. So I should say
doesn't have that form.
free massless free Fermion systems with
At finite
Fermi
density
yeah.
only. So for instance, if you take
Yes.
a massless Dirac theory in 2+1 dimensions, it doesn't scale like this. It has a non-universal area law plus a universal finite term. It's usually nowadays known as the F theorem or something. So it's not quite. So this is not the general form of in particular, of a relativistic field theory at criticality. Even in systems that don't obey relativistic scaling, they don't scale like this.
I see. Thank
So
you.
this is special to the case that was discussed by Joe Van Clesch. Okay.
I see. Yeah, it's just one example of how these violations can happen in higher dimensions. And in a way, I'm following the footsteps of this higher dimensional generalization in the main part of this talk. So one simple way one can have volume scaling of entanglement entropy is to have this strong inhomogeneity where the coupling strength decays as you go from the center of the chain to both ends, so that at each order of the perturbation theory, you have an antiferromagnetic interaction that prefers a singlet pair state, so that each pair of sides with the same distance to the center are forming a EPR pair, so that each of them contribute a unit of entanglement when the system is cut into half in the middle. And I try to generalize, so this is called the rainbow chain by Sierra Latorre and others, and I try to generalize this into higher dimensions. And this I found out the best one can do is to enlarge the local Hilbert space into, for example, for 2-dimensional space into SU3, and then for the same mechanism, each 3 sides in the layer forms a SU3 singlet, and then we add the next order strings, then this strong homogeneity induces effective coupling within each layer, so that they all form a triplet pair. However, if you count the Hausdorff dimension, you see this is still of dimension 1. And you can also see that by the possibility of labeling the label size in a linearly increasing number. And if you for the 1D chain, people found this inhomogeneity in coupling can be mapped to ADS metric in the holography dual. But in this case, in the 2D lattice is transparent that this coupling strength decays with the distance, and the metric is already encoded in the lattice structure. And this can also be generalized into arbitrarily higher dimension, where within each layer you have a simplex that has all-to-all interaction, very much like the SYK model, except that here is SUK symmetric, and it's not the coupling strength is not random, and there's a very nice structure of this Schrieffer-Wolff transformation that you can show this kind of effective coupling in any dimension. But you see this. This gives you a hint of how to get volume entanglement by having this kind of palindrome structure. And however, it also shows that without being translation invariant, it's hard to generalize into genuine higher dimensional lattice. So the cure to this is a translation invariant model that is also called frustration-free, meaning that each local the ground state satisfies the lowest energy eigenstate of each local operator in the Hamiltonian, so that you can identify the ground state just by looking at the Hamiltonian. And in reality, it's more like people have constructed such a ground state that has high entanglement, and then they found the Hamiltonian, apparent Hamiltonian that gives this state as the ground state without knowing about the rest of the excitation spectrum. And this is a popular type of Hamiltonian that people have studied for the AKLT chain and also toric code. And it's also a recurring theme of my own research. So how does this Hamiltonian work? You imagine mapping this spin one chain into a path of up, down, and flat moves. And this is a random walk description of a spin one chain. And however, you can put the constraint that this walk never goes, it's always on one side of the axis, so that it never goes below the x-axis. And this can be enforced by a boundary term in the Hamiltonian that penalizes starting or ending the moves in the wrong direction. And then also by constructing these projection operators to favor the correct superposition of these locally different configurations, all come in the ground state superposition with the same weight. So that if you have anywhere below the axis, and then you can use one of these two kinetic terms that propagates into one of the boundary, and then it will not make the boundary term happy. So in the end, these bulk projectors and the boundary terms pins down the ground state as a superposition of all these kind of Moleskine paths. And from the heuristic picture of a Moleskine walk being very similar to random walk, you see that the average height in the middle is scales as the square root of the distance you have walked, which is which gives you a logarithmic scaling. And Movasa and Schur added enlarged the local Hilbert space with additional color degrees of freedom, where the up and down spins can come in, let's say, two different colors. Then now the leading contribution of the entanglement will come from the matching of color between spins of the same height, so that the entanglement comes is proportional to the average height in the middle, because each unmatched pair within one subsystem will contribute a unit of the entanglement. And this average height again scales as square root of n, so that now you have a power law violation of the entanglement entropy. So this model, these two models are very similar to the rainbow chain that I just talked about, except that it's kind of a diluted version where you don't have the absolute maximum entanglement entropy, but the scaling can still roughly, you see that there is the potential that the entanglement can become larger if, depending on what the average height in the middle is.
Can I ask a nice question? So do these models have continuum limits?
That's a very, very good question. And I think it's better to postpone this question to a few slides later, because there will be more information on that. And if you're not satisfied, then maybe remind me to answer it later, if that's all right. So, so the idea is to have a ground state that actually favors higher height in the middle by rotating these 2x2 bases of these local projectors. And you find that there is some consistency equation you have to obey when you consider multiple ways to reach from one configuration to the other. And one particular translation invariant solution to this set of consistency equations is where you weigh this path by the area underneath, so that you have a ground state weighted by this deformation parameter to the power of this area. And then you can show that there is an entanglement phase transition that as soon as this deformation parameter is larger than 1, you have a volume scaling, and as soon as it's smaller than 1, it obeys area law. There is also a spin half or half integer spin realization of this by replacing this spin 0 with a pair of up-down spins, so that the interaction involves next nearest neighbors, but the phase diagram and the scaling of the entanglement are completely the same. So we show this scaling in a very brute force way at the beginning, but what we didn't know is that this is a well understood object in terms of limit shape and random tiling models. So in 1D, these up-down spin configurations can be mapped to a Young tableau rotated by 45 degrees. And if you take a random average of all these Young tableaus, you see that the most typical shape of this boundary of the Young tableau it has a known curve that is called the limit shape of Young tableau, and it gives the same scaling as the average distance of a random walk after n steps. However, one can have other kind of limit shapes by having a Q deform the measure of these Young tableaus. And in this combinatorial community, this limit shape is only non-trivial if you deform this probability according to the size of the system. Because otherwise, if it is deformed by a constant Q parameter, then it immediately favors the maximum or the smallest Young tableau as it is larger than 1. So in principle, one can have all these kind of average that is between square root and linear, and by having this inhomogeneous deformation. And this also happens in 2D models in terms of lozenge tiling and domino tiling, where there is another more interesting phenomenon called Arctic curve, or in this case, Arctic circle, which says that near the corner of this hexagon lattice, you can only have one kind of these 3 different orientated lozenge, where the fluctuation only happens inside the Arctic curve. So outside is considered frozen. And this also has a limit shape, which for this particular boundary is flat. I'll say more about the definition of the height later, but you already see that this is not enough to get the entanglement that we are trying to find. So the way to do this is to define a model that has a boundary only inside the Arctic curve, and then you enforce the boundary terminations to make the going from outside the optic fur to inside, the height changes in the right direction. So when you generalize this to 2D models, the obstacle we had for a long time is to have a well-defined height notion. As in 2D, unlike 1D, you have multiple ways to count the height difference from one location to another. However, this is intrinsically avoided by this constrained Hilbert space of U1 Coulomb gauge phase. So one example is the 6-vertex model, where going around, you can define a height function whose group becomes the spins, and going around any vertex, the height doesn't change. And likewise for this lozenge tiling, that is also mapped to dimer models on hexagonal lattice. You can also define the height change along the edges of the dual lattice. So to enforce this, so both these local constraints and the boundary condition that you require it to be more or less a constant height. Actually, it alternates between 0 and 1 because it's a discrete lattice. But both of these you can enforce with a local diagonal Hamiltonian, and then you just need to introduce these kinetic terms that relates locally differing configurations by a ring exchange. So you reverse all the arrows of one square, and you require them to come into relative weighted by this Q deformation parameter, and then the same story happens, that the entanglement entropy of half system when you cut the cross in the middle is proportional to the area of the cross-sectional surface. So this height function gives you a definition of this 3D picture, that if you cut the cross in the middle, you get a cross-sectional area, and then you can show that its entanglement is proportional to this area. And also there is integer spin analog of this model, which is also studied in classical STEMMAC in the context of 19-vertex models, where instead of the I through of 2 in, 2 out, you can also have a dashed line that corresponds to spin 0. And you also require the net inflow of arrows is 0. So this gives you 19 possible configurations. And you also require this ring exchange moves that has 9 possibilities instead of 4. But now it only requires the 4 edges of a plaquette. So you are not controlled. You don't need to condition this on the additional third spin outside to make sure that the height doesn't go below 0. And for the hexagonal dimer model, you can also have this picture of viewing the lozenge tiling on 2D lattice as a bird's eye view of a pile of unit cubes from the 1, 1, 1 axis. So now you need to enlarge these dimers into 2 components of colors along the 2 edges of this lozenge that it maps to. And if you take the cross section of either X, Y, YZ, or ZX plane along any plane, you get a dig path, which is what this spin half chains in 1D have, that is matched in color in pairs at the same height. So this is a depiction of the height configuration of this particular boundary. and this is one the lowest height configuration where it bears the name of a rhombile tiling. So you are tiling hexagons of all the same shape instead of lozenges.
Sorry, could I ask again? These models have a good continuum limit?
Yes. So actually, it's still better if you ask in 2 more slides, but I'm getting there. Yeah, in 2 more slides, I hope I'll give a satisfying answer. Yeah, so you have the same mechanism of penalizing color and matching and unbalancing, and also locally different heights configurations with locally different heights are weighted by the volume underneath this random surface. Yes, so as in the square lattice model, when you cut in the middle, you get a cross section, and this Schmidt decomposition, which gives you the correct way to count the entanglement, has a leading contribution proportional to the average area. So this becomes a much harder problem than in 1D, right? We cannot do it in the brute force, but luckily there is a well-known field theory description of these random surfaces in the scaling limit. So these weighted surfaces are described by the partition function that is only depends on the surface tension as a function of the gradient. So if you take the scaling limit where the tiles becomes arbitrarily small, and then for a small region, you have a gradient of how the height changes. And this number of random surfaces for that particular gradient is only a function of the gradient itself. But now we are also weighting these surfaces by the volume underneath them. So you have this kind of competition between these 2 terms. The gradient terms favors the most flat surface, while this one favors the one with a higher volume underneath. By doing this scaling transformation, you can see that in the scaling limit, this as long as you have this linear term in the height, whenever Q is not equal to 1, this always becomes the dominant term, so that when Q is larger than 1, you have volume scaling, and when smaller than 1, you have error law. However, when Q is equal to 1, this term disappears and it becomes a more intricate problem. So this is the problem of the average height of a random surface or Gaussian free field conditioned to be non-negative everywhere inside the bulk. And due to this effect called entropic repulsion studied by Deutschel and Giacomin, this actual average differs from the average you get from the calculating the green function of a Gaussian free field by an additional factor of square root of log L. Basically, that comes into the extremal distribution, so that you have a deviation from the average by an amplitude of square root, but you want even the deviation below that average to be still above the 0 plane, so that the average now needs to be shifted to log L. And that's how you get this log L scaling for this critical point. And this theory also applies to higher dimensions, so that in principle, if you can find the tiling model in 3 dimensions or larger, you also know the entanglement scaling there, which will be LD minus 1 times square root of log L. And
I have a question. In these height models, normally, like in a solid-on-solid model, the theory is invariant under uniform shift of these heights. and your
Right.
term, your no-Q term violates that condition. So there is a preferred. So that means
no,
that you're
I should define this better, but this is this phi is defined with respect to the boundary being a constant zero height. So you can shift the height in your definition of the height on the boundary. You assume it has this zigzag shape along the boundary, meaning that it always fluctuates between 0 and 1. But you can define that to be 0 in the continuous. This is what this is defined relative to the height and the boundary.
I see. Okay, thank you.
And in principle, these tiling models exist in arbitrary dimension, and it's pointed out by Christopher Henley that for all these dimensions, you have a perpendicular dimension where you define this height function in, and in particular in 3D, there's this rhombohedral tiling where you can tile this isocahedral with two different ways. And so since the highly entangled phase is, by the way, did I answer your question about the continuous limit satisfactorily, Pedro?
Yeah. So it's really, you say it's really just a continuum limit of random surfaces where the boundary condition is fixed. And so the system knows about the boundary condition.
Right. So a better way to say this is that it's not a Markovian process. So in numerical simulations, people study these vertex or loop models with this worm algorithm where they, instead of doing this ring exchange move that change a locally smallest tile, they change arbitrarily, they do arbitrarily large loop updates so that it's more efficient. However, this doesn't work because doing this will easily make the height non-negative in some way. So somehow what you can change depends on the surrounding of a larger and larger radius. So there is this non-Markovian nature intrinsic to these boundary constraints. And we know that since this phase is highly entangled, it must be gapless. And there's we find a very simple way to show this by having by constructing a state orthogonal to the ground state by softly violating this color on the boundary. And this only gives a non-zero contribution to the expectation value of the Hamiltonian when this height is, when this configuration has somewhere is touching the x-axis, so that you can relate to another configuration where this color and matching is penalized. However, this comes in areas much smaller than the maximum area by a factor that's exponential to the square of the system size. And in 3D, you can in 2D models, you can construct similar excited states that gives you a dent that's proportional to the volume, so that you now have this Q to the minus L cubed scaling. There is also a holographic tensor network description of the, I'm almost done, so this is the last slide. So you can encode this, you can map each of these dig paths or the spin half configurations by flipping this path and then mark the interface between horizontal arrows and vertical arrows. So that in the bulk, you only have these 5 different kind of tiles, which are the non-zero elements of a tensor that you contract inside the bulk. While on the boundary, you have these 3 different types of ancillas, and this corresponds to the physical external lags that maps to the actual physical degrees of freedom. So you see that this this actually makes sense, because if you cut anywhere in the middle, you can count, you can get a upper bound on the entanglement entropy, and you see because of this 2D bulk, you always have a maximum that's up to the volume. And it's possible to generalize this for the 2D lattice, where you combine these 5 different configurations in 3 cross sections, and it turns out there are only these 2 ways, and you can also do the similar mapping by flipping these surfaces, although there is some additional work on this that is still open question. So so we have shown that this boundary and local constraints can facilitate extensive ground state entanglement entropy, which is rare, by using these height models that has additional color degrees of freedom. And also by performing this frustration-free deformation, you can have an entanglement phase transition as you tune the deformation parameter. There are a bunch of things one can ask about the fragmentation and the scar states, which people both studied for the 1D model and also the slow dynamics, which were actually part of the inspiration due to Lammercraft, who studied the classical lozenge tiling models. And at the critical point, the tensor network I just proposed isn't optimal because it doesn't give the correct upper bound on the scaling, but it's possible to optimize with some renormalization scheme, as people have did for the 1D model. And you see the 3 phases of this 2D lattice model is exactly the same as the measurement induced phase transition that is quite popular these days. So one thing that that's on my radar next is to somehow construct a exactly solvable model for this measurement induced phase transition on this platform. And finally, thank you for your attention, and thank to all my collaborators who have enlightened me in so many different ways. So the next slide will be the picture slide. If you want to ask any questions before I move there.
So what's in your opinion, the main conclusion of all this work? What have we learned about entanglement from this?
I'm sorry, I didn't hear the question.
What have we learned about entanglement from your work? What's the main conclusion?
Oh, what have we learned about?
When you discuss different models and how the scaling happens and what kind of scaling they show and so on, but what's the
right? So
the take home?
I don't know.
Okay.
The take home message is that you certainly need an additional space that is not in the lattice space that facilitates this kind of entanglement. So you need this.
But that induces an inherent non-locality in the quantum dynamics.
Yes, I guess one can say that. It's not in a very rigorous way, but that is the heuristic picture, I would say.
I mean, in a local field theory or in local problem Hamiltonian, I would expect in general to have an area law or a volume law in states which are when you don't have integrability. But
right, but only if it's gapped. If it's not gapped, then there isn't any theorem forbidding this.
So there is no theorem. Well, in principle, there should always be an area law, which is not universal. That depends on the regularization of the theory. It depends on the type of lattice you use or what have you. Even if you take a relativistic field theory, you always expect an area law, which is not universal. It's usually in the corrections to the area law where you see the non-trivial scaling of the continuum field theory. Not in the area law per se, which is not, I mean, because the area has a prefactor that has to cancel, has to have units, and therefore it cannot possibly be universal. The same is true with all of these power laws that you discussed. They're also not, I mean, they have a prefactor which is not universal. So there is a question,
Right.
where is the universality of all of this?
I mean, it's not exact, but I think well, the universality in the CFT case, it comes from this central charge that counts the effective number of degrees of freedom, right? Here, I think there is also the factor, although it's not exact, the prefactor is the logarithm of the number of colors. So it's also in a way counting the degrees of freedom of the local Hilbert space. And the scaling remains the same as you change the prefactor, but if you want some sense of universality, I guess, within this small class where you have different number of colors for the same model, there is this prefactor. It's definitely not that universal as the critical point described by CFT is. I wouldn't say that.
Okay.
Rogerio, you had a question?
Yeah, so thank you for the talk. I'm not from the area, from this field, but can you just say if there are any predictions that you made that can be verified experimentally?
There isn't immediately, but I can try to make some. So the problem with realizing this in optical lattice or codatom is that it's hard to realize these projection operators, which what it does. So it has two eigenvalues. It squares to itself. It either has energy 0 or 1. And so it's hard to realize these interactions that pins down particularly one state and don't care about what the rest of the excited states. However, in the spirit of this AKLT chain and how effectively it describes the antiferrometric spin 1 chain, you can actually do things to the projector. And for example, you can discard these diagonal terms, and then it becomes something much more similar to the Heisenberg chain, which is possible. Well, at least relatively more realistic to implement in some case. And it is possible, in my opinion, that the entanglement scaling and correlation wouldn't drastically change. I mean, I don't have a lot of confidence of saying that, but this is in general what people do. So why do I bother to construct this tensor network description? In principle, it's supposed to be useful for numerical simulations for Hamiltonians that are not exactly this, but similar enough to this, so that it gives you some approximate simulation that is good enough, although not in this particular case that is exact. But so this is in general, if you want me to make some prediction, I would say Hamiltonians similar to this, but are not exactly the same as this, may have roughly the same behavior, and those may be possible to realize in optical experiments.
Okay, thank you.
Don't show the last slide just so we can.
Yeah, so maybe I can say a few things. Entanglement, as I said, is continuing to be one theme of my research. Although now I'm moving more towards this non-equilibrium measurement-induced phase transition in these quantum circuits. So partly this is motivated by the important role that entanglement plays in scalable quantum computation. You definitely don't want too much of that because of the propagation of error, but you also want to utilize them enough to take advantage of the quantum supremacy. So there is some trade-off that, and it's I'm not an expert on that yet, but this is something that I want to go more into in the future. And another theme is to chatter the territories of the middle ground between solvability and integrability. So my understanding of this whole spectrum models is that you have two axes. So one axis, the vertical axis here, is the what I call frustration-free axis, where you can get some information about the ground state or solution of the Hamiltonian by something local in the space dimension, in the coordinate space. And the orthogonal axis is the integrable axis, where you have things that are local in the momentum space. So in general, any eigenstate you can describe by integrating over arbitrary momentum. But for these integrable models, you have only a finite number of discretized momenta so that you can just sum over the permutation among them. That is this diffractive scattering, but very little is known about when this violates and what happens when it softly violates or violates only in part. And I already have one work about this, but the other direction is so for these frustration-free models, most of the time people only can solve the ground state, and at most they know a tower of very few a set of measure zero of excited state that obeys this spectrum generating algebra. But so my goal is to figure out what the rest of this space is, and maybe find more models that have this kind of structure. And also, I have a few other works relating to topological order, integrable field theory, etc. But instead of forming a clear theme, I would say the more coherent way to put this is I tend to find some new collaborations with local people when I move to a new place, and that's how I develop these other interests. So that's also something I'm looking forward to.
Thanks. I guess I had I'm also not from the field, so I just have some basic questions. So you talk about entanglement phase transition. Is there something intermediate between area scaling and volume scaling? Or is it always this discrete jump from one to the other?
No, so I wanted to say earlier that so in this combinatorics community, people study this deformation that depends on the size, but for them they have the luxury of having a varying system with varying sizes. So you just consider a different lattice for a different Q parameter, and you can always find this deformation that gives you a non-trivial limit shape, however much you want it to be tuned by this alpha exponent. But for this lattice model in condensed matter physics, we don't have a varying size, but still you can mimic this by making the deformation parameter inhomogeneous, meaning closer to the center you have meaning this deformation parameter decays to 1 as you go from the center to the boundary or vice versa, so that when you take into account the average of the whole system, although the system size is fixed, if you cut, as you cut at different locations in the middle, you can still see the entanglement grows with different scaling behavior according to how you tune this deformation parameter. So in principle, any power law scaling you can get by this inhomogeneous deformation.
And that's in any
But
dimension.
that's a very good question. Yes. Well, if you can define such a model in any dimension, you can. I'm quite certain you can do this inhomogeneous deformation to get this.
Other question? I can ask another question. So when you discussed the field theory, you had some result that, at least you stated some result above 3 dimensions. It goes like square root of log L. That's an analytic result, or that's just a simulation result, or how?
Yeah, it's an analytic result, but it's not my own result. It's the result by this series of papers by Loisho and Zaitoni. So this is the trivial calculation one can get from the correlators of Gaussian free field, but they have this additional factor that so in principle, what the result that you get in dimensions higher than 1, you have this additional factor of square root of log L that you multiply to these results, and that's how you get this log L and square root of log L. And these are very rigorous results in this way.
What is the intuition behind this extra square root? Is there a simple explanation why we get an extra square root of log L?
Why is log L? I mean, the intuition is that you need to take into account these extremal deviations from the average. But why is square root of log L? I'm afraid I can't answer on top of my head. Probably a few months ago when I just look at this paper, I can, but no, I don't have a quick answer to that. I'm sorry.
So the statement is that the 2-point function would go like log L squared, right?
The 2-point function, the square root of 2-point function, which is a standard deviation, is square root of log L. But then you have this correction of square root of log L that in the end gives you log L for the height. And then it's a 2D system, so you need to multiply by L to the D minus 1. So that's how you get this L log L.
Sorry, okay.
Another question? Do you have any questions for us about ICTP-SAIFR or?
Yeah, so I look at the website, the list of people. Is that webpage up to date?
List of which people?
Local researchers or
so
faculty members.
I think it is. I can look at it again just to make sure. So we're inside the graduate physics department of UNESP, which is called IFT. So IFT has about 15 researchers. So we are a small subgroup of them. So probably you looked at the ICTP researchers, right? Is that correct?
Right.
So if you
ICTP-SAIFR
that's right. So there are about 5 of us. So I guess there's myself, Pedro, Rogério, Ricardo Surani, and we have some well, I don't know if you call senior postdocs. It's called young investigator. Danilo Liarte is also here. So he does I guess it's related to statistical mechanics or condensed matter. And then there are also people doing condensed matter. There's Alexandre really harsh, and other people are mostly doing particle physics, things like that. I don't
I see.
think the closest to you would be who? Danilo Liart, is that right?
Yeah, possibly. But there are other people in Brazil, maybe in the Sao Paulo area, that will be
That's
closer.
in São Carlos, there's
Carlos in particular.
yeah.
I see. And this position can supervise the PhD students? Or?
Yeah,
Or-
so the way the supervision works is you can either get a grant from the state funding agency or you can get grants from the university. So it's, we encourage you to supervise students. And also postdocs, so we have postdoc positions with the grant. So, yeah, the science of best fellows usually have one or sometimes even two postdocs that come from our grant. So that's not an issue, I guess. There's some small amount of teaching. It's not quite voluntary because we'll use the teaching to evaluate for tenure, but usually it's on advanced courses. So we just have graduate students.
Oh, that's good. Okay.
Not any undergraduate.
Yeah, advanced courses are fine.
Yeah, that's right. So we have about 70 students, about half are PhD and half are masters, maybe a little more PhD than masters.
I remember a long time ago I read something like about Brazilian students by Richard Feynman. Have you do you know what I'm talking about? I don't think it's a very positive comment on Brazilian students. Is that true, or has
Can
changed
you remind me
over
what the
the
statement is?
That was in the 1960s, you know, there has been some 60 years between the time he wrote that and now.
So it's no longer like that.
I'm sorry.
I would say.
Are you talking about Feynman's comments or what was
Yeah.
Of course, everything has a little bit of truth, but I think certainly there's less memorization than there's less emphasis on memorization than there was then, but there's still probably too much classes and too little time for free thinking here. But I think it's.
But this university gets the best students of the country at least, right?
Yeah.
Is it the best physics?
I think that's true. Theoretical physics, yeah. We don't have experiments, but I think theoretical physics we get. And I think.
But
yeah, obviously.
Students are also interested in condensed matter or.
Yeah. So it depends a lot on the advisor. So obviously they come. So in Brazil, when you come to do graduate work, you already have to have an advisor. So they're looking for an advisor when they choose where they want to study. So it depends on, obviously, depending on who is available, that will attract different students. But yeah, Danilo has gotten good students. So I think it really depends on how much emphasis you make or the professor makes to have students. Yeah, I get very good students. Pedro gets very good students. I'm sure Rogério and Ricardo get very good students. Most of them get postdocs abroad after they finish. So, right, it's not at the level of Harvard or Princeton, but it's probably at the level of, I don't know, average university in the U.S. I don't know, Pedro, Ricardo, or Rogério wants to make.
I have a question. Israel was your advisor, your PhD?
Yes.
I see.
And also Jeffrey Teal. I'm
Jeffrey,
co-advised by both of them.
Jeffrey was my postdoc. Okay.
I know, yeah. He said many good things about you.
Okay, well, that's a good thing to know. Okay.
Okay,
And also I briefly overlapped with Paul Findlay before he left.
Okay. He's in Oxford now. Yeah.
okay, so what is going on now is we're making a short list, and the short list would be people who are going to invite to visit. I assume you've never been to Brazil, is that correct?
No.
Okay. So probably within a week we'll be able to tell you your status.
Okay.
Does anybody else have
Thank
any
you.
question? So your position at CISSA is until when?
It's until up to December this year, so I have enough time.
Very good. Okay, nobody has any questions. So thanks very much, Sal.
Thank you.
Thank you. Thank you. Thanks everyone for being
Very
here.
interesting.
Yeah, thank you. Bye.
Bye.
Bye-bye.
Bye.
Eduardo, do you want to stay on for a few minutes?
Yes, I will stay on. Yes.
Let me just stop the recording.
Oh, everyone left.
Okay.
Rogerio left and